onto the hydrogen. So because the hydrogen has migrated from position 1 to 5, we'll call that a 1,5 hydrogen shift, because this end of the sigma bond, where the hydrogen is, the sigma bond stays attached to that. The migration, that's slightly disappeared there, is suprafacial. It migrates across the top face of the system. So it starts on the top face, ends on the top face. If it started on the bottom, it would end on the bottom. If you go to a 1,7 shift, where the molecule can form more of a spiral system, then the under thermal conditions, and we'll see why this is allowed in just a moment, the 1,7 shift, 1, 2, 3, 4, 5, 6, 7, is anterofacial. That means if you start on the top, you end up on the bottom. So it goes on the opposite sides of the conjugated system. So that's an observed experimental fact. We need to think about how that works. So those are 1N shifts, so 1,5 or 1,7. And we need to think about how that might be explained in molecular orbital terms. So we need a frontier molecular orbital treatment to decide whether suprafacial or anterofacial is allowed, or to explain the results I've just shown. So for a 1,5 hydrogen shift, the result is that it's suprafacial. So how can we understand that? So heating here is just moving across. I've shown it from left to right this time, or like the last one was right to left, but basically equilibrium across here. Of course, you can only tell if something is happening if the two ends of the system are differently substituted, or some other kind of labeling there. But this is the sort of basic prototype system. So how do we explain this? We treat it as if it's a pi 4 plus sigma 2 cycloaddition. We know that it's going to be suprafacial, so we'll call it pi 4s for suprafacial, sigma 2s for suprafacial again. We treat it as if it is a cycloaddition between a diene here and a CH bond that's moving here. So let's choose, it turns out to be simpler if we choose the HOMO of the CH bond. So there is the HOMO of the sigma bond, which is, so it's the bonding orbital of the sigma bond. That means we must choose the LUMO, the lowest unoccupied orbital of the diene, and that's this one, a single p orbital there, two in a pair there, and then a different one here. So that's the LUMO of the diene. And now you can see we need to, this H has got to form or can form a good interaction with this end of the remote end of the pi system, and the other part of the sigma bond can form a good interaction to form a new pi bond here. So both the new pi bond and the new sigma bond give a favorable orbital interaction. And we can generalize that like this. So each time we'll consider the HOMO, the sigma bonding orbital, and the one we've just seen is the 1,5 shift, and you can see both parts of the sigma orbital, the contribution from hydrogen and the sp3 hybrid contribution from the carbon are the same phase, and the two ends of the LUMO of the diene are the same phase. So that's suprafacial, that works on the same side. If you go to the 1,7 system I showed, then this is the LUMO of a triene system, and then you look at the two ends and you see they're not the same phase. So if a sigma bond is going to add across the two ends of this system, then it has to be anterofacial. The sigma bond has got to add to one end on one face and the other end on the other face. If you go to a 1,3, so this is a rearrangement of a hydrogen from one end of an allyl system to the other, where there's only one double bond involved and one sigma bond, and you look at that, you can see that that would also have to be anterofacial, there, and that's geometrically impossible, so you don't see it under thermal conditions. The 1,5 suprafacial, that's fine, because you can imagine going from one face across to the same face, that's easy to imagine. And the 1,7 system only works because of the length of the system. Because this can be a spiral, so one end of the system can be underneath the other end of the system. So it needs to be long enough to be anterofacial. You can't do that with only one double bond involved. And that fits with the orbital picture here. So 1,3 could be anterofacial, except that geometrically that's impossible. 1,5 suprafacial is possible geometrically. 1,7 anterofacial is also possible geometrically. And you can go on I don't know if there are any examples of those, but 1,9 and 1,11 and so on. It's alternating suprafacial, anterofacial. And those are the results for thermal reactions, but as I showed for other cycloadditions, or this is a sort of imitation cycloaddition, then you get the opposite allowed and disallowed conclusions for photochemical reactions. So that begins to illustrate how you might look at sigmatropic shifts in a hydrogen shift, so they're all 1 something, 1,3, 1,5, 1,7. They're not so useful in synthetic terms for making complex molecules like natural products. Much more useful in organic synthesis terms are the so-called 3,3 sigmatropic rearrangements. So now if we break a sigma bond, not only do we count around 1/2 to where the new bond is formed, but instead of this top position being just a hydrogen, if this has more atoms, then we count round the other half, the other component or the other side of the sigma bond as well. So you count from the two ends of the sigma bond that's breaking, in each case around to the new sigma bond that's forming, and that's where the 3,3 description comes from. Break this bond, form that bond, so that's a 3,3 sigmatropic rearrangement. Now I've not drawn any curly arrows on there to indicate electron flow, but you can do if you look at the two key cases that are used in synthesis would be the so-called Cope rearrangement, where the system is all carbon, and so I've drawn the arrows there showing electron flow, and of course the electrons, it's a pericyclic reaction, so I could draw that in either direction. In other words, the directionality of electron shift doesn't mean anything, it's just to help you put the bonds in the right place. Cyclic transition state, reorganization of electrons, so it fits into our pericyclic reaction family. An alternative there is where there is an oxygen in the framework, and you can imagine still the same kind of reaction going on, but when you do the rearrangement, of course in the Cope case, the two, in the simple prototype case, the two isomers are the same energy, so there's nothing to choose between them without any substituents there. But in the Claisen case, it will go in the left to right direction because you're breaking a sigma bond, forming a new one, but you're also forming a strong carbonyl double bond. So there is a driving force for the Claisen rearrangement to go towards the carbonyl form. So like most pericyclic reactions, the direction of the transformation depends on the thermodynamics, on the energy of the starting and finishing materials. Okay, so those are the two systems we'll be looking at in more detail. And if you want to do a frontier molecular orbital treatment of this, again, you treat it as a cycloaddition. And one way, there are various ways of doing this, and one way that I'm going to show you is to treat it as a 4-electron plus 2-electron cycloaddition. To do this, you define two 3-carbon units. So you imagine it's effectively, oh, that's a mistake. That should be a single bond. I'm sorry, not a double bond, a single bond. So yeah, this one here, that's an error. That's a single bond. Should be a sigma bond that's breaking, sigmatropic reaction. So we'll define two 3-carbon pieces. You imagine where the sigma bond is partly broken and partly formed. That gives you two fully bonded 3-carbon pieces. Let's imagine one of those is deficient in electrons and the other is excess electrons. So we'll imagine it like an allyl cation, a 3-carbon cation is one component, and an allyl anion, a 3-carbon anion, will be the other component. And one way of looking at this is to use the HOMO of the 4-electron allyl anion and the LUMO of the 2-electron allyl cation. So there is two 3-atom pieces, but if one is an anion in this treatment, that's got 4 pi electrons or 4 electrons involved, and the cationic piece will have just 2 electrons involved. So in fact, in this case, if you look at the allyl system, the 3-carbon system, and look at the orbitals, if it's an anion, the HOMO is occupied, and it's of the three orbital combinations in a 3-carbon system. This is the middle one. So in the anion, it's occupied, and it has a node at the center. In the cation, that same orbital is unoccupied and is the LUMO. So the LUMO, the 2-electron imagined component of the allyl cation, looks exactly the same as the HOMO of the allyl anion, but one is occupied, one is unoccupied. And if you draw those the right way up, then you can see that we get constructive overlap at each end. As long as we do it through a suprafacial, you imagine a suprafacial way of approach, and that gives you effectively, if you imagine new bonds forming here, this is like a chair cyclohexane. So we're imagining a chair transition state, and in orbital terms we're imagining a 3-carbon cation approaching a 3-carbon anion, and we're thinking of it in a 4 plus 2 electronic arrangement. Now there are some other ways of looking at this, but of course they all come to the same conclusion, that this is an allowed reaction, and this is one of the pictures you can use. So as long as you can have that chair type of transition state, this should be an allowed process. So if we look at the all-carbon case and the energetics as I said earlier, the prototype with no substituent is energetically neutral. In other words, the two isomers have the same energy, so it's reversible. How can you bias that to go in one direction predictably? Well, one way is to use strain relief. So here is an example of that. A cyclopropane, this is a natural product that is built with appropriate double bonds on it. One is a simple vinyl system and one is a longer chain, but they both have a double bond adjacent to the sigma bond in the cyclopropane. And of course you have bond angle strain in the cyclopropane. So there is a driving force here, and you can see at 80 degrees in refluxing carbon tetrachloride, this does ring open to give the ring expanded product, which is also a natural product. So it's believed that actually nature with enzyme catalysis does effectively the same process. And if you look at what might be going on here, this is the vinyl system, which I've labeled 2 and 3 in green. You can just about see that. This is the cyclopropane here, where the sigma bond between the two positions labeled 1 in green and 1 in red is breaking. And then here's atoms 2 and 3 in the bottom side chain, which is the other original pi bond that's involved. And you can see if I show, there's the new bond forming between 3 green and 3 red. So if you look all the way around, the electronic rearrangement is in a chair form. What's driving that forward is, of course, the relief of the bond angle strain in the 3-membered ring. There are other ways of making sure this reaction goes the way you want. And one of those is to have a substituent which biases it. So the so-called oxycope rearrangement, where you have an oxygen substituent. Here is the basic backbone, 2 double bonds separated by a single bond. That's the sigma bond that's going to break. One of those sp3 carbons has a hydroxy group, an oxygen substituent, here a hydroxy group on it. And this will go at 220 degrees. Now, the first part of that process is not favorable energetically, but what makes it favorable is that one of the rearranged double bonds now carries the OH substituent, so you've generated an enol through the process. Of course, all the bond angles are wrong there in the way that I've drawn it, but I've just drawn it so that it looks like the starting material, but this would not actually be that shape. But when you form that enol in water, this tautomerizes to the keto form, and that, of course, so the formation of that carbonyl group is what drives this reaction forwards. So we can bias the energetics by having a substituent that will provide a lower energy in the product. Now, actually, if you take the oxycope rearrangement and make the hydroxy group into an anion, for reasons that are not really properly understood, that accelerates the reaction many, many, many times faster. So here is an example where we have the cope rearrangement system here, 1, 2, 3, 4, 5, 6. So this vinyl group can twist underneath so that that position and that position can join together. If you heat that in a sealed tube at around about 200 degrees Celsius for several hours, it will rearrange. But if you do that, so that works, but clearly that's not a very easy reaction to carry out. And if you have a complex system, more complex than this, you're likely to get some decomposition at those kind of temperatures. But if instead you use potassium hydride to deprotonate this alcohol group to give the alkoxide, then using 18 crown 6 to keep the potassium cation in solution, make this homogeneous, then at 0 degrees with a half-life of an hour you can do the reaction. So you imagine several hours at 200 degrees to 0 degrees in half-life of an hour, then that's a significant acceleration. Of course, you don't get the ketone directly, you get an enolate of the ketone. In fact, you get a mixture of the two. This is equilibrating under the reaction conditions. You get the enolate with the double bond in either of the two possible positions, and then you can work that up by adding water and acid to form the enol, which then tautomerizes immediately to the ketone. So there's something special about forming the anion there, which is not properly understood, but it is a way synthetically of accelerating this, and once you neutralize this strongly basic system here, then you end up with a ketone, you end up with the same product as you would from the simple hydroxy group reaction. So those are ways of biasing the energetics of the coat rearrangement to go the way you want, strain relief or a suitable substituent. One of the reasons that these sigmatropic rearrangements are useful is that the transition state, being a chair or chair-like in terms of the geometry, means that you can use all the boat and chair axial and equatorial preferences that you learn about for cyclohexane. So the chair-like transition state means predictable stereochemistry. Equatorial substituents are preferred wherever possible, just as you would expect for a cyclohexane. So here's an example. Let's take this substituted system that's going to do a coat rearrangement. I've just put on a substituent there, I'm not specifying what it is particularly. You could imagine a chair, a pseudo-chair type transition state. All that's missing is the new sigma bond that's forming, or that's a conformation. There would be the transition state. You could either have that with the substituent R group in an axial position, or you could imagine an alternative ring-flipped form where the R group is in an equatorial position. Imagine those conformations going through to these transition states, then the transition state with the R group in the axial or pseudo-axial position is going to be higher in energy because of 1,3 diaxial interactions, just like in any cyclohexane type system, so it's going to be higher energy than the equatorial version. And if you follow that forwards, if it had been in an axial position, then that would give you a Z double bond, cis double bond, in the newly formed double bond carrying the substituent group, whereas the lower energy transition state would lead you to the E double bond, trans double bond. And because the equatorial substituent is preferred, this lower transition state is preferred, so in the product the E double bond is preferred. So you can, what this is telling you is you can predict, knowing that you can draw the transition states in a chair-like form, you can predict what the geometry is going to be in your products, the stereochemistry is going to be. Here's another one which is a sort of classic example. This example was more or less invented to show that the chair transition state works. So here we have two methyl groups on the backbone, And when you heat that up, you could get the EZ diene, you could get the EE diene, or you could get the ZZ diene. You get almost exclusively the EZ, so one double bond E and or trans and one double bond Z or cis. You can work out why that should be, because if you draw this as if it's going to be sort of ready to be a chair transition state, then with these two methyls on the same side when drawn like this, that means one must be axial and one must be equatorial. Follow that through the transition state, then that means that one double bond is going to be Z and one is going to be E. So that's the only combination, E and Z, of the two product double bonds that is available via the chair transition state. So the other two are not going to be possible from this starting material because of this conformation leading to this transition state. If you have the corresponding molecule where drawn ready for the coat rearrangement, that conformation shows the two methyls on opposite sides. You could get again EZ or ZZ, or you could get EE, and that's the one that is the major product. This one is not, the EZ is not possible via a chair form. Then we have two that are possible via chair forms, the both trans or both E, and the alternative is the both cis, which is both Z. Well, if you draw the chair form here, the more stable chair form, with the two methyls on opposite faces of the pseudo-cyclohexane, then they could both be equatorial. That's clearly the favorable one. Follow that through to that transition state, and that will give you the both E double bonds. On the other hand, if you imagine a ring-flipped form of that, it's possible to have the two methyls on opposite faces, but to be both axial. And that would give both double bonds forming cis or Z and Z. So, not surprisingly, the double equatorial is more stable transition state than the double axial, so you get much more of the EE than you get of the ZZ. So this is a classic example that was used to show the effectiveness of thinking about a chair or pseudo-chair transition state. But what it does mean is that in any case where you're going to do a coat rearrangement, you can use a chair transition state to predict the stereochemistry. The alternative here is, or the other possible 3,3 sigmatropic rearrangement I want to focus on is the Claisen rearrangement, where we don't have to worry about the directionality of this because the forming of the forming of a carbonyl group here to here drives this forward. All we've done is change one carbon in the coat system to an oxygen. It's still thermally allowed, as we showed earlier. So it's effectively an allyl vinyl ether. And what it does is it forms a sigma bond and a carbonyl group, so it forms a bond adjacent to a carbonyl group. So you're transferring a substituent from oxygen to carbon. And this can be very useful in synthetic sequences. The carbonyl product is about 84 kilojoules per mole, more stable than the starting enol ether, and that's essentially, as I say, the formation. What's driving that most is the formation of the strong carbonyl group. You can imagine a chair-like transition state, just as I was drawing a couple of slides ago for the coat rearrangement, And what that means, once again, is you get predictable stereochemistry. So here would be, so from this situation with different substituents, I'll show in a minute why I've labelled this one Y rather differently, but substituents in various positions, you can follow that through. There would be a chair-like transition state where it's just a bond between the two double bond termini that is the sigma bond we're forming. The CO bond at the back there is one we're breaking. There's the chair transition state with a sigma bond breaking and a sigma bond forming. And depending on what stereochemistry you have at that position, what geometry you have in the alkene, depends on where things are situated in the transition state, and therefore where they end up in the product. So here, if this R1 is equatorial in that conformation, then it ends up as giving you a trans or E double bond. If this substituent is opposite or trans to the oxygen, then you end up with it in equatorial position there. So effectively, you're transferring, you're generating new stereochemistry here and generating new double bond geometry there, and it's all predictable according to the according to the chair transition state. Now, you may have come across the Claisen rearrangement before, where there isn't a worry about stereochemistry and so on. The classical Claisen rearrangement, this is where it was discovered, was in the benzene system, where one of the double bonds involved, the vinyl double bond, as you might say, the one directly attached to oxygen, is part of a benzene ring. So I'll just put this in just to remind you of it, although it's not so important from stereochemical terms. So phenol allyl ethers will do an aromatic Claisen rearrangement like this. Of course, that produces a system where you've broken the aromatic character of the benzene ring. So we get a further factor, as well as that double bond, the carbonyl double bond forming. Well, actually, it's driven by reforming the aromatic system by proton shift from carbon to oxygen. In those cases, if the ortho position is blocked, the initial Claisen product can then do a cope reaction. And okay, that looks geometrically unfavorable, but you've got to think that this group here is actually above the benzene ring. So this carbon on the substituent can reach the bottom there because this is sticking up and over the ring, although it's not drawn to show that. You can then go to the para position and then it can rearomatize. So there we can have a Claisen followed by a cope rearrangement. So two successive 3-3 sigmatropic shifts. That usually takes quite high temperatures if it's uncatalyzed. So just reminding you of that. Actually more useful is the Claisen rearrangement where it's not on aromatic rings, and more useful still where you have other variations. Now, let me go back. The reason here that I had instead of using R1, R2 and R3, I put a Y group there is because that substituent there ends up on the new carbonyl group. So we can have various functional groups formed there depending on what that Y substituent is. So here's a way of doing the Claisen rearrangement using an allyl derivative, an allyl ester. At the moment, that doesn't look like it's ready to do a Claisen rearrangement. We're one double bond missing. So how do you make the double bond here? Because then you'd have the right setup for a Claisen rearrangement. How you make the double bond, the extra double bond you need, is to form the enolate. So the original version of this was the enolate Claisen. So now our Y group is an oxyanion. You need a strong base, so that's lithium diisopropylamide, low temperature to stop it doing anything else. And you've got the enolate, so you've got double bond character here. You can do the rearrangement as you allow, so you form the enolate at -78, and as you allow it to warm to room temperature, it rearranges, and then the oxyanion, the Y substituent I showed in the general case, is part of a carboxylate anion.
So the movement of electron must be in the anti-clockwise direction.
Sorry?
Here in the Claisen rearrangement, the movement of electron must be in anti-clockwise direction, or it may be...
It could be either way.
Either.
Sometimes you might look more sensible drawing it in that direction, but you can actually draw it either way. It's still believed to be just a cyclic rearrangement of electrons with no directionality. So the only reason I've drawn it that way, that's my choice. There's no particular reason for that. Some people might argue that drawing it the way I have is better or makes more sense because you're pushing electrons towards that oxygen, but it really doesn't matter. So what you're doing is you're forming a carbon-carbon bond next door to a carboxylic acid functionality. These enolates are not particularly stable, so this reaction can be problematic. Sometimes as you warm these enolates up, they do other things. So a development of this was made by Professor Ireland to make the silyl ethers of the enolates, and those are then a little bit more stable, so this is a more controllable reaction. So you form the enolate in the same way, then you treat it with a silylating agent. I haven't specified which one. It could be trimethylsilyl, it could be any of the other silylating reagents, tertiary butyl dimethyl, doesn't really matter. They all have slightly different stabilities, but it depends what you want to do later. If you then allow the silyl, or you warm up the silyl enol ether, you can actually keep these silyl enol ethers in some cases, and you warm them up and it does the rearrangement. You end up with a silyl ester, and if you want the acid, of course, that's easy to hydrolyze by treatment with water. So that's a slightly better procedure to do in the lab than just warming up the enolate. You can notice here that the stereo control I've used is exactly the same as I showed in the general case, and you can predict it therefore by drawing chair-like transition states. So I've not drawn them here, but they were drawn a couple of slides ago. So these behave in just the same way as the ether Claisen rearrangements. There are two more variations I want to show you. One is the Johnson Claisen rearrangement, and this is using ketene acetals. So what he did here, I haven't got substituents on, but if you had substituents, it would follow the same chair-like transition state. So you take an allylic alcohol, you react with an orthoester. Again, I haven't specified which orthoester, could be methyl or ethyl, doesn't really matter. That allyl alcohol, this needs a little bit of acid catalysis. That allyl alcohol exchanges for one of the alkoxy groups on the orthoester, and then another one eliminates to form a double bond. So you end up with a ketene acetal here. So if this was a carbonyl here, it would be a ketene. So this is an acetal of a ketene. One of the OR group, one of the oxygen groups is what was in the original orthoester. The other oxygen substituent is what was your original allyl alcohol. Do that rearrangement and you end up with a alpha beta gamma delta unsaturated acid derivative. So the bond you're forming is this carbon-carbon bond here is the one you're forming. Something that's rather like that was proposed by Professor Eschenmoser, where he used the Y group is now an amino substituent, and it's a different kind of ketene derivative. So again, you take an allyl alcohol, you treat with this orthoamide. The allyl alcohol with a little bit of acid catalysis substitutes for one of the alkoxy groups. Then the second one eliminates to form this double bond. And then it's set up to do the Claisen rearrangement. So again, you end up with this carboxylic acid derivative with a gamma delta unsaturation, and you've made this carbon-carbon bond, which effectively is from the alpha to the beta position relative to the carboxylic acid derivative. So in the Johnson system you end up with an ester, and in the Eschenmoser system you end up with an amide. And if you think about it in terms of the original allyl alcohol, the new carbon-carbon bond has been formed at the opposite end to where the alcohol is situated. If there is a substituents on there and some stereochemistry, then you will get stereo control, or you can get stereo control, which you can predict via the chair type transition state. Okay, well that's all I wanted to say about sigmatropic rearrangement. So that's the end of this session. In time to take now a break. And what I propose to do, or what I will do in the session after the break and before lunchtime, is want to have a tutorial session, so an interactive session, where I'm going to set you some problems. And in fact, I believe Professor Singh circulated the, did he circulate some PDF files to you last night? Yes. Okay, which will, so the PDF file number 5 will be this one we just had, and the PDF file labeled tutorial 1 will be what we're going to look at next. So there's some problems in there about pericyclic reactions, which we can work through together. So this is practice for you with systems that you haven't seen before. Okay? So I suggest, so if we now take a break and we can resume again around 11:30, and then we'll run through for an hour or so leading up to lunchtime with that tutorial session. Okay? Thank you.